Hello, students. Today, we're going to connect all the ideas from the chapter Atoms and Molecules. The goal is to build one clear picture in your mind, which will really help you prepare for your exams.
You know, sometimes this chapter can feel like it has so many small, separate ideas, right? But actually, they are all beautifully connected. So in this session, we're going to build those connections step by step to make everything perfectly clear.
Here's our simple roadmap for our revision today. We'll start from the very beginning, with the ancient philosophical ideas about matter. Then, we'll see how those ideas led to real scientific laws. After that, we'll look at Dalton's famous atomic theory, get to know the key particles like atoms and molecules, and then learn how to write chemical formulae, the language of chemistry. And finally, we'll wrap up with a solid game plan for your exams.
All right, let's start at the very beginning. How did people even come up with the idea of atoms in the first place?
It's quite amazing, really. Long, long ago, thinkers from completely different parts of the world had the same fundamental idea. Here in India, Maharishi Kanad talked about Parmanu. He said it's the smallest particle of matter, or padarth, that you just can't divide any further. And around the same time in Greece, a philosopher named Democritus suggested the idea of atoms, which in Greek means uncuttable or indivisible. Both were imagining a final point, a tiny particle you just can't break down anymore.
Now, for a long time, these were just ideas, just philosophy. But then, science came into the picture. Scientists, especially Antoine Lavoisier, started doing careful experiments. And from these experiments, two very, very important laws of chemical combination were established.
Okay, the first law is the law of conservation of mass. Now, this is something you must remember very clearly. It simply states that mass can neither be created nor destroyed in a chemical reaction. In simple terms, it means that whatever mass you start with, the reactants, will be exactly equal to the mass you end up with. The products. Nothing just disappears. And the second law is the law of constant proportions. This one says that in a pure chemical substance, the elements are always present in a definite proportion by mass. The classic example is water, H2O. It doesn't matter if you take water from a river, from the sea, or make it in a lab. The ratio of the mass of hydrogen to the mass of oxygen will always be 1:8. It's a fixed rule.
So think about it. Scientists now had these two solid laws based on experiments, but they didn't have a theory to explain why these laws worked. Why is mass conserved? Why are proportions constant? This is where a brilliant scientist, John Dalton, enters the story.
This is John Dalton. He came up with a scientific theory about atoms that could perfectly explain both of those laws we just talked about. He basically took that ancient idea of the atom and gave it a proper scientific foundation.
So, here are the main points, or postulates, of Dalton's atomic theory. Let's look closely at how they explain the laws. Look at the second point. Atoms are indivisible particles which cannot be created or destroyed. That's the perfect explanation for the law of conservation of mass. Now, look at points 5 and 6. They say atoms combine in simple whole number ratios and that the kinds of atoms are constant in compound. Well, that's exactly why we have the law of constant proportions. See how beautifully Dalton's theory connected everything?
Okay, so now that we have Dalton's theory as our base, let's get to know the main characters in our story, the actual particles. We need to be very clear about what we mean by atoms, molecules, and ions. So here's a big question. An atom is incredibly, incredibly tiny. You can't see it. So how on earth do you weigh it? It's practically impossible. So scientists came up with a really clever solution. They decided to measure its mass relative to something else. And what did they choose as their standard? They chose a particular type of carbon atom, carbon-12. And they said, okay, we will define one unit of atomic mass, which we call 1U, as exactly 1/12 the mass of one carbon-12 atom. It's just like the fruit seller example. If he uses one slice of a watermelon as his standard weight, he can weigh all other fruits relative to that slice. We do the same thing with atoms.
Now for your exams, especially for solving numerical problems, you will need to know the atomic masses of some common elements. This table shows the most important ones. Please, make a note of these. Hydrogen is 1, carbon is 12, oxygen is 16, and so on. Knowing these by heart will save you a lot of time.
Next up, we have molecules. Now, most atoms, you see, cannot exist independently, so they bond together to form stable groups, and these groups are what we call molecules. A molecule is the smallest particle that can exist on its own.
Good examples are the oxygen we breathe, which is O2, or a water molecule, H2O.
All right, what about ions? Well, atoms are normally electrically neutral, but what happens if this balance is disturbed? If an atom loses one or more electrons, it becomes a positively charged ion, called a cation. For example, sodium becomes Na+. On the other hand, if an atom gains an electron, it becomes negatively charged, and we call that an anion. A good example is chlorine, which becomes Cl-.
Okay, so we've met the particles, atoms, molecules, and ions. Now let's learn how to write about them. It's like learning the grammar for the language of chemistry, which is written in chemical formula.
The most important concept for writing formulae is valency. Simply put, it's the combining capacity of an element. A really easy way to think about it is like this. Valency is the number of arms an atom has to hold on to other atoms. For example, hydrogen has a valency of 1, so it has 1 arm. Oxygen has a valency of 2, so it has 2 arms to form bonds.
And this brings us to the very useful crisscross method. It's a simple 4-step process. Let's take magnesium chloride as an example. First, write the symbols, Mg and Cl. Step 2, write their valencies below them, 2 and 1. Now for step 3, the crisscross part. The 2 from Mg goes to Cl, and the 1 from Cl goes to Mg. You get Mg1, Cl2. And finally, we simplify. We don't write the number 1, so it becomes MgCl2. Simple, right?
Once you have the formula, you can calculate its mass. We call it molecular mass or formula unit mass, but the calculation is the same. It's just the sum of the atomic masses of all the atoms in the formula. For water, H2O, we have 2 hydrogen atoms and 1 oxygen atom. So the calculation is 2 into 1 plus 1 into 16, which gives us a total of 18U. It's just simple addition.
All right, we have covered all the core concepts. So for the final section, let's talk about your exams. How can you take all this knowledge and make sure you score full marks in this chapter? Let's make a clear game plan.
Okay, please pay close attention. This is your exam game plan. Number 1, you have to memorize the symbols and valencies. Table 3.6 in your textbook is very important for this. Number 2, practice. Practice writing formula and calculating mass until it becomes second nature. And lastly, please be careful and avoid common mistakes. For example, the symbol for cobalt is CO, not CO. These small details matter a lot.
So as you study this chapter, always remember this. Chemistry isn't just something in a textbook. It's happening all around us. The entire world, everything you see and touch, is made of these atoms.
So, let's end with this question for you. What is the one thing from this chapter that you will practice right after watching this? Just one thing. Decide now and do it. Remember, with this kind of focused revision, you are very well prepared. Don't be anxious, stay calm, be confident. All the very best for your exams.